Hey, Dr. Clark here, and in this preview video, we're going to be looking at section 5.1 on initial value problems for linear models. Let's take a look. So first, we're going to start with just a standard spring mass model. So you got a mass on a spring. The differential equation we've seen before is my double prime plus ky equals 0. But here, we're really going to think of it as sort of in the xy plane, or in the x direction, basically. So it's kind of oscillating this way. And so we're going to be thinking of x as the dependent variable, t as the independent variable. So we'll be looking at this differential equation. And in the previous chapter, we already saw that you can solve this thing. And in this case, you just get a sine and a cosine function. So c1 sine omega t plus c2 cosine omega t is the general solution. And omega in this case is root k over m. It's just based on the coefficients here. And the solving of that comes from running this through the characteristic equation and so on. We call this simple harmonic motion or free undamped motion. Okay, the word free means we don't have a forcing term on right-hand side, so it's just oscillating freely, in other words, and the undamped motion just means there's no friction term, so there's no, it's just the spring and the mass by itself. And then you can just think about properties of sine and cosine. There's a period, there's a frequency, and so that's some of the things we're going to look at. Is we already know how to solve this thing, so what properties can we look at that come from the solving of it? Okay, the next natural thing to do would be to put on friction or a damper into the model so that friction term bx prime shows up here. We're still free, we still have no right-hand side there, but that damping term is proportional to velocity. So the faster that thing is moving, the more fluid it's plowing through, so the more friction you get. So that's kind of the idea. You want to imagine this thing is like setting in an aquarium, and as that mass moves through the water, it sloshes around and that slows it down. Okay, and then we've seen before as well, when you run this through the characteristic equation, you get a quadratic. If you put that in the quadratic formula, you can either get sort of two real roots or two complex roots. And so in the two real roots case, you just get decaying exponential functions like so. If you have complex roots, then you end up with these decaying oscillating terms, e to the negative at sine of omega t, e to the negative at cosine omega t, and the a and the omega depend on the coefficients m, b, and k, and it comes from the quadratic formula, essentially. Okay, we're calling this free damped motion, right? So free in the sense that there's no forcing term, but damped now that we have the friction term. And you still have this sort of quasi-period in the sense that the oscillations do have a period to them based on the sine and cosine, and so that t is 2 pi over omega. So we call that a quasi-period because it's not exactly a periodic function. Okay? And then the third thing we can do, and we'll explore this more in class, of course, is put right-hand side. So put some sort of forcing term. We call that either forced or driven motion. And you can do that on either an undamped or a damped model, but you can imagine them putting a little fan on there that can, maybe push one way or push the other way or push both ways or something, so that you could have a constant force or a variable force, and so you've got some sort of system like this. And in general, you're going to get some kind of solution that is a combination of a homogeneous solution and a particular solution. The homogeneous solution we've already seen in the previous two slides when you just set right-hand side to 0 and solve it. The particular solution is related to that forcing term in a way we've seen as well. And what we want to do today, and in class coming up, is to think about how particular forcing terms lead to particular solutions, and then how those things relate with the interaction between these two things. So that's kind of the goal of this section, is really going deep into this one particular model, the spring mass damped model. And then if you understand one thing deeply, that kind of helps you understand other things later. All right, so look forward to seeing you in class, and we'll kind of put all the details into these things. This is the general framework we're going to look at, but we'll put the details in, and it should make sense there, and based on our previous knowledge of how to solve these second-order linear constant coefficient differential equations. So we'll see you there, and I look forward to it.